In the previous session, we introduced the CCR model, which in fractional form is this model. This model could be changed to linear programming model, as you see. We gave some theorems and definitions with example that there was one input and one output. Now we give another example that has two inputs to produce one output, that all the outputs are one, and we have 6 DMUs here. So for each DMU we should solve the CCR model. For example, if we write for DMU A, the linear program, the CCR model for DMU A is maximize theta equal to U, because we have one output and the output value is 1, so the objective function for DMU A is U by 1 or U. The constraints for each DMU, we have constraints A to F, but this constraint is only for DMU A because its first input is 4, the second input is 3. So we have 4 V1 plus 3 V2 equal to 1. This is a linear programming model and can be solved with any linear programming solver or indeed by the simplex method. If we solve this model, we will give these optimal values that shows DMU A is not efficient because theta star is less than 1. Of course, we can solve the model, this model, as we will show later, geometrically, but here the optimal solution is as you see. For this optimal solution, the constraints of D and E, when you put the optimal values, these constraints are in equality form, which means if you multiply 2 by the first component of V star plus 4 multiplied by the second component of the V star, it will be equal to U star. You can put this value and you see that the equality is for D and E, so we have the reference set For this optimal value, as you see, it is D and E. Similarly, we can write the linear program for DMUB. As you see, we maximize theta is U by the output of DMUB, that is 1, so we have maxima U. The first constraint is 7 because the first input of B is 7. V1 plus 3, the second input of DMUB, V2 equal to 1. The other constraints are similarly, so we have this constraint because DMUA and the variable, all the variable U, V1 and V2 are positive. We can solve this also with any model. The unique optimal solution is obtained here. So the CCR efficiency of B is less than 1, so B is also inefficient, and its reference set is C and D. This means if you put these optimal solutions in the constraint, then you have equality for the constraints of C and D. Note that for each DMU we maximize its efficiency, so the efficiency is obtained by using the best weights for that DMU. So when we have, for example, V1 star as this and V2 star, which their ratio is 4, this suggests that it is advantageous for B to weight input X2 4 times more than input XA in order to maximize the ratio scale measured by virtual input to virtual output. Likewise, for DMUF, we have this model, this linear programming model with this optimal value. Here, theta star is equal to 1, but V1 star is 0. In the definition, we said we should have theta star equal to 1 and the weight should be positive to say the DMU is efficient, but here V1 star is equal to 0. The question is, if this is the if we may have another optimal solution with positive weight. So we assume we have an optimal solution with V1 equal to, for example, epsilon, which epsilon is positive. If we put epsilon instead of V1 in the model, that means here, so from the first we have V2 is equal to 1 minus 10 epsilon, and by putting these values to the constraints, we have this which means u is less than or equal 3 minus 26 epsilon, and so on. So we want to find the maximum value of u when u is less than or equal to these values. So the biggest value of u is the biggest value of u with these conditions is the optimal value of theta star. So we can see the maximum of u is the minimum of the right hand side. So the maximum value of u will be 1 minus 2 epsilon, because the other are bigger than or equal to this value. But if epsilon is bigger than 1, that is the value of theta star, is always less than 1. So also we have the value of 1 for the optimal theta star, but this value is obtained only for the optimal solution that the first input weight is equal to 0. So f is not CCR efficient by definition to 1, and f is CCR inefficient. Indeed, we give the name of weak efficient to this kind of DMU. By solving the CCR model for all the DMUs, we have these results. Indeed, for A, the value of inputs and output, this is its optimal CCR value, model value, which means theta star, the reference set, and the optimal weights. For this example, as you see from the figure 2.2, E, D, C are efficient. F is not efficient because C has the same input 2, but its first input is less than F. So C dominates F. So F is not efficient. For A, if you minimize its inputs, so A will be compared with the convex combination of E and D, so its reference set will be D and E, and its efficiency is less than 1. The same for B, we use D and C to determine its efficiency, as we explained. Here we solve the previous example geometrically. Note that for each DMU, indeed for all DMUs, we have these constraints that are common. If we divide the both sides of these constraints, noting that u is positive, we will obtain the following inequalities. We want to show the example graphically in a two-dimensional graph. So if we divide this by changing variable, here we have only two variables in compare with these values that these constraints that we have three variables. So these constraints are common for all DMUs. Now we can show the feasible region of these models easily. Indeed, we have 6 constraints with 2 variables, and you know how to determine the region, the feasible region. For example, for the first constraint, we first put 4 multiplied by the first variable plus 3 to the second one equal to 1. This is a line that if you determine, for example, the value of the first variable when the second one is 0, that is this point, and when the first is 0 and the second one will be this one, this is 2 points in the line correspond to A. Note that when we put V1 divided by U equal to 0, so V2 divided by U will be 1 divided by 3. That is here. And similarly, when we put V2 equal to 0, the value of V1 by U, the first value, would be here, 1 divided by 4. So this line shows all values of the first and the second variable. For that we have 4 multiplied by the first plus 3 multiplied by the second one would be equal to 1. But in this figure we want to know the values that determines by the first constraint. We put, for example, you know many ways to show this. For example, we put the first and the second variable equal to 0, and we will see this is not satisfied in these constraints. So the region that the first constraint shows is the up of this line, because you see that the origin will not satisfy on that constraint. We will do the same for the other constraints. So for C, for example, we have this line. For D, E, F, and B, and you see that the origin will not, the origin doesn't satisfy to any of these constraints, so the side opposite to the origin shows the values of variables that satisfy in the constraint. In addition, these variables are positive, so the constraints show this visible region that is shown here. So we have this visible region, and for each DMU we want to, for example, for DMU D, maximize U when we have this. We divide both sides by U, we have this. We know maximizing U is equivalent to minimizing its converse. So we want to minimize T when T is equal to this value. This means this is the objective function which should be minimized in this region. But this can be solved easily, can be minimized easily, as you know from your linear programming course. Indeed, this is the objective function. You can compare this and you see that this is the right hand side of the constraints corresponding to DMU D. So we want to minimize this when the value of these variables are in this region. You know, for this purpose, we can, for example, give a number to T. This will be a line, and we know which side maximize and which side minimize this. For example, for T equal to 1, we have the line D. This line, if you move up, the value of T will be more, and by moving it down, the value of T will be less. So the less the minimized value of T is when D pass 2 points P2 and P3, and on this line the value of t is equal to 1. So the objective function of model will be 1, and the optimal weights correspond to the segment between P2, this point, and P3, this point. All of these are optimal solutions of model which solves the CCR model for DMU-D. So DMU-D, when T star is 1, so 1 divided by U star would be 1, so the optimal solution of the CCR will be 1 with, as you see, positive weights, because U is positive, and here, as you know, none of the values of V1 and V2 in all the optimal solutions, none of them are 0, and both are positive. So we can say D is efficient. If we consider other DMUs, for example, if we take A as another example, we have to maximize U when we have this constraint, that this is equivalent to minimizing T, that T is this. But here also we have minimizing a function with two variables in a two-dimensional space. Here also you see, you can compare T is indeed this, that is correspond to the constraint A. So we want to minimize this. When this value is equal to 1, we are in line A. Here you see this value is not feasible. Indeed, T equal to 1 is not feasible. And when we minimize the value of T, its optimal solution will be P3, this point. So, as you see, this is T star. The optimal value is bigger than 1 because it is in the side that the value of T's become bigger. So when T star is bigger than 1, the converse of the efficiency of DMU A would be less than 1. So A is not efficient, and its optimal value can be obtained easily. Indeed, if you put the constraints of D as equality and the constraints of E as equality, by this in the D and E, which means this is for D, put this equality and put this equality. So you have two equality constraints with two variables that its value, its solution will be obtained easily, and this solution corresponds to P3. So for this optimal solution, the constraints correspond to D and E are in equality. So for A, the reference set is D and E. Indeed, you can solve the model and you can find its reference set. As you see, the optimal solution is obtained here. For the others, and you see for A, this point is optimal. We can have the same for all other DMUs. Now consider DMU F. For F, you see P1 is the less value of T correspond to P1, and its value will be 1. So the efficiency is also 1 because it's converse of this. And here you see the value of the first variable is 0, and the second one also is V2 is 1. So, and this is the only optimal solution. Indeed, F also its CCR efficiency is 1. It is obtained only for an optimal solution that the first V1 value indeed is 0. So there is no other solution with positive weights. So F is weak efficient. For C, you see also P1 is optimal, that the first weight is 0. But we have also P2 with positive weights as other optimal solution which optimize the efficiency of C. And we have the same for E. So E and C and D, as you see, have optimal solutions with positive weights and their value is equal to 1. So these are efficient. A and B have the optimal CCR efficiency less than 1. F has the optimal CCR efficiency equal to 1, but it's obtained only for a solution that at least 1, here V1, one of the weights is not positive. So F is weak efficient, B and A are CCR inefficient indeed, and the other C, D, and E are efficient. So this is The summary of Chapter 1: we defined virtual input and output, its ratio when it is maximized, when the others are less than or equal to 1. This CCR model defined the CCR efficiency. Please solve the problem of this chapter and send your solution to me.